In this lesson, we are going to review the electric vehicle example model. You will learn about the vehicle powertrain model, the powertrain control module or PCM, and mechanical load models. You will also learn about the modeling approach for the charging station, which accounts for the needs of grid-to-vehicle and vehicle-to-grid operation modes. Both the charger and the EV are implemented using detailed power electronics models. First, let's navigate to the electric vehicle example using the Typhoon HIL Example Explorer. You can open this example by clicking the Open Model button. For this demonstration we are going to use a Typhoon HIL 404 device. The model consists of three parts: a grid and a residential load, a charging station, and an electric vehicle. The most interesting part is the electric vehicle subsystem. Let's see what's inside this subsystem. On the left side you can see the vehicle's battery, modeled here as a lithium-ion battery. From the Battery Properties window, you can define properties of the battery and also view the battery's discharge characteristics. This electric vehicle model also includes a 2-level 3-phase inverter, an LC filter, and an induction machine. The 3-phase inverter is controlled using the internal modulator control type. For the induction machine, you can see that electrical and mechanical properties are defined on the component mask. The control algorithm used to drive this induction machine is field-oriented control. You can see how this control algorithm is implemented by looking under the mask of the control subsystem. The controller used to drive the induction machine is implemented in signal processing. This controller is used to model mechanical processes within the electric vehicle which determine motor behavior. The input to the motor controller is the machine torque, which is output from the induction motor component. The output of the controller is the reference speed for the induction machine. As you can see in this example, the signal processing library can be used to implement multi-physics models. You can find more information about this mechanical model in the application note linked in the Materials tab. In the charging station subsystem, you can see that charging station behavior is modeled using the battery inverter microgrid component. Unlike the EV powertrain model, which was built from scratch, the battery inverter component comes as a ready-to-use component from the microgrid library. Looking inside the battery inverter component, you can see that the power stage comprises a detailed power electronics model and the controller includes grid forming and grid following modes. The power stage includes a DC link, a 3-phase inverter, and an LC filter. Various voltage and current measurement components are placed at key locations throughout this subsystem. A controller used to drive the inverter model is also included in the battery inverter component. The DC side of the battery inverter is connected to the battery in the electric vehicle subsystem. Parameters for the battery inverter component are set on the component's mask. Using this and similar plug-and-play library components, you can significantly reduce model development time for system-level power electronics and microgrid applications. In the HIL for Microgrids course you will learn how to quickly build microgrid models using libraries of high-fidelity DER models. The last subsystem in this example is used to model the grid and a residential load. In the grid and residential load subsystem, you can see a 3-phase voltage source, a grid impedance, a contactor, and a residential load. The nominal power of this residential load is 20 kVA with power factor of 0.95 lagging. Now, let's compile and load this model. In this example, you will see the electric vehicle model used to simulate a driving mode where the induction machine behaves as a motor, a regenerative braking mode where the induction machine behaves as a generator, an EV charging mode where the charging station is charging the vehicle battery, a vehicle-to-grid mode where the vehicle battery provides support to the grid, and an uninterruptible power supply mode where the vehicle battery supplies power to the residential load. Now let's run the simulation on our HIL device. Open the dashboard and start the electric vehicle by clicking the Start-Stop button. You can see from the indicator LED that the electric vehicle is now on. Let's simulate accelerating by moving the speed reference slider to 70%. You can also see that a slider is included to simulating braking. With the speed reference at 70%, you can see that the speed and motor RPM have increased along with the total distance traveled. The bar graph at the bottom shows the battery state of charge. On the right side of the dashboard, you can see electrical torque, electrical power, and average consumption. In the power torque graphs subpanel, you can observe the electrical torque and active mechanical power operating points. Now let's move on to the second operating mode, regenerative braking. In the case of regenerative braking, the kinetic energy of the electric vehicle is used to charge the battery. You can see that with the new speed reference, the Typhoon Regen LED is on, indicating that regenerative braking is active. You can also see that the battery is charging. Before turning off the EV, use the braking slider to set the speed to 0. Let's set the braking to 100%. After EV is stopped, turn off the EV by clicking the Start-Stop button again. The next operating mode is charging mode, where the battery is being charged through the charging station. To change operating modes, you can use the buttons in the operating mode presets group. To select charging mode, click the EV charging button. You can see the current operating mode indicated in the status group. In the DC fast charging station subpanel, you can see more detailed set points and measurements for the charging station. The charging power is currently set to 150 kilowatts. You can select the desired charging power using the PREF slider. The next operating mode is vehicle to grid. Select this mode by clicking the vehicle to grid button in the operation mode presets group. You can see the new operating mode reflected in the status group. In this mode, the battery supports the grid by providing power. You can see that the battery is currently supplying 150 kilowatts to the grid. You can also see that the battery is now discharging. The active power reference for grid support can be changed in the DC fast charging station subpanel. The last operating mode is uninterruptible power supply or UPS. In this operating mode, the EV battery will supply power to the residential load. The load in this example draws an apparent power of 20 kVA at a power factor of 0.95 lagging. You can see that, in this mode, the load is being supplied from the battery. You can also see that the battery is discharging. To disconnect the charger, click the Disconnect the Charger button. In this lesson you learned more about the electric vehicle example model, including microgrid library components and multiphysics simulation using the signal processing library. You also gain familiarity with the operation modes of the electric vehicle example model. Thank you for watching.